across the lab, from the Von Ryan lab to the Osborne lab at Drexel, with Dante Freeman, who's here to revisit Henneman's science principle in Drosophila. Welcome.
Thank you very much. Good morning. My name is Dante Freeman. I'm a second-year medical student working in the Osborne lab at Drexel. Today I'm going to talk about our work visiting the Henneman size principle and the motor system of Drosophila. To produce smooth and controlled movements, the nervous system needs to adjust the muscle force over a wide range. It does this partly by recruiting different motor neurons. When only a small amount of force is needed, the so-called slow motor neurons are recruited first. As force demands increase, intermediate motor neurons and then fast motor neurons are recruited. The question is, what establishes this recruitment order from slow to intermediate to fast motor neurons? Elwood Henneman first proposed this relationship in 1957 based on experiments he did on the cat motor system. He noticed that the size of motor neurons increases from slow to intermediate to fast. Over the following decades, size-ordered recruitment became one of the most established organizing principles in motor control. The classical explanation assumes that motor neurons within a motor pool receive broadly shared synaptic drive, and that recruitment order then emerges from differences within motor neurons themselves. Smaller motor neurons have higher input resistance, so the same synaptic current produces greater polarization. As drive increases, slow motor neurons reach their threshold first, then intermediate neurons, then fast motor neurons. This provides an elegant explanation for how common input can produce orderly recruitment based on a motor neuron's intrinsic excitability. And importantly, identical input is a simplifying assumption and it's not demonstrated in every single motor pool. Most evidence for the size principle originally came from vertebrates, although size-ordered recruitment has also been demonstrated in invertebrates as well. In 2020, work led by Anthony Acevedo and John Tuttl's group identified 3 Drosophila tibia flexor motor neurons spanning slow, intermediate, and fast positions within the motor pool. These motor neurons produce progressively greater force. They also show the expected input resistance gradient, with the slow motor neuron having the highest resistance and the fast motor neuron having a lower input resistance. Also, resting membrane potential and other physiological properties also vary along this hierarchy. So, is the case closed? The system looks as though the size principle predicts. But do these motor neurons actually receive equivalent synaptic drive? What's nice is that Drosophila gives us a way to look at this question at a deeper level. With electron microscopy, we can reconstruct detailed morphologies of identified motor neurons and map individual synapses onto their dendrites. This means that we no longer have to treat synaptic input as an unknown common signal. We can directly examine which premotor neurons contact each motor neuron and how many synapses they're making onto each motor neuron. When we looked into the connectome, we found something counterintuitive. Here is the slow motor neuron with its input synapses, which are colored by its presynaptic neuron. And then here is the fast motor neuron, which is recruited later. You'll see it has a much larger dendritic tree, and as we saw earlier, it's like less excitable. Yet, the fast motor neuron receives substantially more synapses than the slow motor neuron, including those synapses which are shared from the 133 premotor neurons shared by both cells. But synapse number does not tell us how strongly those inputs depolarize each motor neuron, because we know that their morphologies and their passive properties are significantly different between each. This leads to our central question: how does synapse number and intrinsic excitability interact to shape motor recruitment? To address this question, we developed connectome-derived biophysical models of the slow and fast motor neurons. To do so, we create skeletons from the electron microscopy mesh data. Further, we defined a putative spike initiation zone based on the work that was published by Henneman and others. Next, we used electrophysiology data, and we fit our model's responses to replicate the behavior of those neurons. We could then test how anatomical inputs are then transformed into voltage responses. Importantly for this talk, I'm just going to focus on passive models, not actively firing models. So we started creating simulations. We first wanted to understand what happens when the slow and fast motor neurons receive broadly the same synaptic input. Here, we simultaneously activated all synapses from the 133 common premotor neurons that are shared by both the slow and the fast flexor motor neuron. Despite their different resting membrane potentials and morphologies, they reach a similar absolute membrane potential at the spike initiation zone, which tells us that scaling a shared input doesn't grant us selectivity and recruitment. And so the outcome may depend on which premotor neurons are activated to bring that motor neuron to threshold to be recruited. So we wanted to examine each of these premotor neurons individually. So we simulated that. We simulated each individual premotor neuron activating to the motor neuron and measured its EPSP at the spike initiation zone. As we see here, premotor neuron B for the slow flexor creates a greater effect on depolarizing it, and premotor neuron A creates a less substantial effect. But this is reversed in the fast flexor, where premotor neuron A has a much stronger effect than premotor neuron B. So this shows us that individual premotor neurons can preferentially depolarize different motor neurons even though they contact both cells. So we established that there's bias and we wanted to quantify it. So we quantified this premotor neuron bias across each of the 133 shared premotor neurons. Each point on this axis represents one premotor neuron. The axes show the EPSP amplitude in the fast motor neuron as well as in the slow motor neuron. So as we can see, points above the axis, those premotor neurons create a greater depolarization in the slow flexor, whereas points below that axis create a greater depolarization in the fast flexor. One thing we found is that even though all these inputs are shared between the fast and the slow flexor, they're functionally biased, such that certain premotor neurons activate one motor neuron more or the other. We also found that the amplitudes for the fast flexor vary more greatly than in the slow flexor. We also color-coded this because we were interested in how synapse number affected these results. And what we did was we took the ratio of the total synapses and compared those ratios against each other such that they're actually comparable. And what we see is that while synapse number does play a role, it doesn't fully explain the differences between premotor neurons with one bias or the other. For example, if premotor neurons favor the fast flexor and that was due to a greater ratio of the synapses, we'd expect points like A, everything on the right to be red, and then everything on the left to be blue. And while that's true to an extent, it doesn't fully explain what we found. So we had another question. If it's not synapse numbers, could the location of where we're putting these synapses on dendrites be controlling how this differential depolarization is occurring? Here, we plotted the average distance of each premotor neuron synapse from the spike initiation zone against that depolarization we measured at the spike initiation zone. So what we see here is in both motor neurons, the slow on the left and the fast, more distal synapses produce less depolarization at the spike initiation zone, But one thing we found was that attenuation is stronger in the fast plexer such that it's a greater slope. So premotor neurons that synapse closer cause a greater depolarization, premotor neurons that are further create a lesser depolarization more strongly in the fast plexer. So we find that synapse number as well as dendritic location shape the functional influence of a premotor neuron to the motor neurons. So we wanted to test how input frequency affects these two motor neurons. For each premotor neuron, we activated all of its synapses at a set of different frequencies to measure temporal summation. What we found is that the slow motor neuron is more sensitive to temporal summation, and this is consistent with its slower membrane time constant. And then we found that in both neurons, plateau amplitude will increase with frequency. And we also found that they're pretty much parallel, and this is pretty much true for both of them and how they respond. Such that while the fast motor neuron curve is slightly shifted upwards, in both curves they run parallel, and thus input frequency scales the responses similarly rather than simply scaling them according to their input resistance. Okay, to summarize, I hope I've convinced you that shared premotor inputs don't necessarily provide equivalent functional drive, and that additional synapses onto the fast motor neuron partly offset its lower intrinsic excitability, but don't fully explain it. Don't fully explain orderly recruitment, per se. And at the same time, individual shared premotor inputs can preferentially depolarize either the slow or the fast motor neuron. And that synapse number contributes to this bias, but neither synapse number nor location can fully predict it. And that input frequency also scales the plateau responses fairly similarly between both motor neurons. Together, these results show us that functional drive emerges from the interaction among premotor activity, circuit anatomy, as well as postsynaptic biophysics. Our next step is to add active properties or firing properties to these motor neurons, and then test how these subthreshold responses are going to affect our spiking and our recruitment. I would like to thank everyone in the Osborne lab, especially Dr. Osborne, for her guidance. I want to also thank Anthony, as he provided a lot of the original code, and I want to thank Howard for the algorithmic improvements, and Omika for working with the active properties, which I will be presenting on at the Society for Neuroscience. So thank you.
For the individual synapses, were they all modeled equally? Like, I'm trying to assess, like, how you determine the postsynaptic response from it. Is each synapse that you put in there equal?
His question was, for the synapses we modeled, were their inputs for current conductances equal? And the answer to that is yes. The differences, we believe, are partly due to their placement on the dendritic arbors, and then differences in the input resistance, as well as just other biophysical properties based on our fitting with the electrophysiology data.
So as a follow-up, do you think there's differences in synaptic dynamics and not postsynaptics, or like incapacitatation for synaptic expression between fast and slow motor neurons?
So his question was, do we think that the differences in these synaptic dynamics are due to facilitation or other things? I would say we haven't specifically looked into that, but that's definitely something we're interested in. Like specifically, I think not exactly to your question, we're interested in classifying these synapses as inhibitory or excitatory based on an image recognition model we found.
Have you thought about neuromodulators and whether they might change their recruitment over their constant inputs?
Gentleman's question was, have we thought about neuromodulators and how they would affect the recruitment and input responses? We have not specifically looked into that, but that sounds like a great thing for us to research. So, yes, we will look into that.
So you started off appropriately enough the modeling by determining the unitary TSP amplitude. involves either a continual increase in the amplitude of successive responses or a diminishment of the successive responses. And so if you considered factoring into your models the possibility that different inputs, even if they're firing at the same frequency, are evoking different pattern responses to repeated activity in the postsynaptic motor neuron?
His question was regarding how are we factoring in the frequency, like the hertz of inputs, because that's more biologically relevant than just a single activation. We're starting to run simulations like that. This simulation here, we simulated each premotor neuron activating at a set of different frequencies. So we did the 25 hertz spiking frequency, so activating the motor neuron at that rate, and then all the way up to 100, 200, and 400. So we're starting to look into this, but this created a lot more questions. So one thing I'm interested in is like specifically how these slopes change. So how each neuron responds differently to different frequencies, and if we can model that a little